Okay, physical science time. Is this the marker I want to use? That's the first question. Is this the marker I want to use? We're talking today about magnets. Remind me, this is a review, remind me of the four fundamental forces. Please say them of the universe. Please say them in order from the strongest force in the universe to the weakest force in the universe. What's the strongest force in the universe? Now listen, there are forces that are like you pushed your sister down the stairs, right? But that is fundamentally, it is going to fall into one of these categories. We'll talk about that in a second, I hope, if I can remember. But there are only four fundamental forces of the universe, four forces that together make up all the other forces that we experience. What's the strongest one? Yep, strong nuclear force. What's its job? Okay, to be strong. And to exist in what part of the atom, if you had to guess? The nucleus. The nucleus. When I say job, I don't mean that these little guys go out and get applications. Obviously, these are non-anthropomorphized quantities. They don't have agency. They don't have conscious thought. So they're not thinking things like, man, like a woman with a job, so I got to go get one. They think nothing. They just exist. And the strong nuclear force exists in the nucleus of an atom. And its function, that's a better word, its function, thank you, Miranda, its function is to glue together the nuclear particles. What are the nuclear particles? We'll learn about this in more depth when we get back from Christmas break. What are the nuclear particles? What particles are in the nucleus of an atom? What two particles? Of the three subatomic particles, you should know this, I think. Protons and what else are in the nucleus? No, neutrons. Protons and neutrons are in the nucleus, and so they are glued together by the strong nuclear force. That's its job. That's its function. What's the next one? Electromagnetism. Can you guess already on this list which of the four fundamental forces of the universe includes what we call magnetism? Electromagnetism. You got it. Electromagnetism deals with all charged particles. It is the force between all charged particles or any charged particles. And when I say charged particles, that's kind of what we talked about in the last chapter. Remember, we had that equation, Coulomb's law, that related the charges to separate charges and the distance between them to the force of electromagnetism between them. Okay? What's the third strongest? The weak nuclear force. I have been quoted before as saying that this one is spooky. I was going to say this is the most poorly understood of the four forces, but that's because I understand it the most poorly of the four fundamental forces. This one's function is to realize the stability when a subatomic particle changes from a proton to a neutron or a neutron to a proton, and they become more stable through that. And that causes, or is one of the causes of nuclear radiation, which we'll talk about probably towards March, sometime around Easter. And the weakest is your old boy, gravity. Again, these are in order here from strongest to weakest. I hope you know what those adjectives mean in this context. It means that the force itself, obviously, let me think. Let me give my little magnet here. Oh, would you go get me one of the really strong magnets too, please, Josie? One of the, like, those neodymium ones, the silver-looking ones. This is a pretty strong magnet, though, and this is a pretty weak magnet. This little dinosaur magnet here. Here I have two magnets. So the magnet does not. You see that the magnet does not pick up the dinosaur. Do you see that? But I thought you told me that electromagnetism is stronger than gravity, so I just proved you wrong. Is that right? No, there's other things at play. Remember, gravity depends on the masses of object and the distance between them. And why is gravity? When I talk about the gravity of this little dinosaur, what am I also referring to? What's preventing it from coming up to the magnet? Earth, the Earth's mass. And so we have a great big mass, as well as a little kind of small mass. But together, those make a greater force than a pretty weak charge. That's what causes magnetism. And a moderately weak charge, which also causes magnetism. But if I get it close enough, I'm decreasing the, what, as I go down? Distance between them, yeah. So if you remember, okay, this just really not a good magnet. It's actually sticking to the chair instead of the dinosaur magnet. It's how bad the dinosaur magnet is. Nice. Okay, well, pretend I use the chair as an example the entire time instead of the dinosaur magnet, because this dinosaur magnet is buns. There we go. What force is holding the dinosaur magnet on there? Yeah, electromagnetism, what we call the magnetic force, and it exists because of charges inside of an object, I guess you could say. So here we have a dinosaur magnet. This is not a dinosaur, so don't even make fun of me if I don't draw a very good dinosaur. This is a dinosaur magnet, and within this dinosaur magnet are particles. What's it made out of? Particles. What do we call those particles that the dinosaur magnet is made out of? And everything else is made out of? Atoms. We call them atoms. And the atoms are generally neutral. They're generally electrically neutral, but they're made of protons, which are positively charged, and electrons, which are negatively charged. And sometimes, in some substances, those charges, those charged particles, can arrange themselves in such a way. Maybe it'd be better if I just drew this in a different way than that. It has these invisible, what we call magnetic domains in it. So in the same way that the magnet, that bar magnet, or this bar magnet, this bar magnet, has a color. It says north is red, south is blue. What's this made out of? What's this made out of? Magnet stuff. Like the dinosaur magnet, they are both made of, I'm asking you very simply, atoms. And those atoms exist in, again, magnetic domains. So you can't see them. Look at this. Do you see the things I'm drawing on here? No, you don't see them. But sometimes, especially in the elements iron, cobalt, and nickel, there are others, but especially in those, there's some down here, neodymium and praseodymium. But especially in these three and a couple down here, sometimes those atoms with the charged particles, protons and electrons, arrange themselves in such a way that they're all kind of pointing the same direction. Every one of these little magnetic domains, in fact, every little atom within this has its own little north and south pole. If we get even closer, here's the blown up version. Every little atom within there has a north and south pole, which has to do with the spin of the electrons. Now, not every atom has a north and a south pole, but because of what this is made out of and the way they have been arranged, these have a north and south pole. So the atoms they are polar, meaning they have Polar Express. You got it. Yep, it's about the movie Polar Express. That's because it's a Christmas. This is a Christmas episode of Mr. Crime Science Channel. No, they're called polar because, thank you, Brinley. Thank you for being the only human being in here. They're polar because they have poles. The Polar Express is called that because it's going to I assume, I've never seen it because it looks awful, but I assume it's going to the North Pole because it's about Santa Claus. Yeah, and so it's going to one of the poles of planet Earth, because planet Earth has this thing, the same as the little dinosaur here. Here's your girl Earth, Finland, Canada's up here for some reason. What else? Canary Islands, obviously, we've got to include those. Anyway, Earth, in the same way as the magnet and the dinosaur magnet, has a north, which I should do in the same color as the others, north and south pole. It's polar. Some atoms are polar, meaning that they have poles. And when some atoms that are polar arrange themselves, BT dub, what atoms are polar? Sometimes Some of them, which ones? Usually iron, cobalt, and nickel are the ones that your book talks about. There are others, but usually iron, cobalt, and nickel. So some atoms are polar. When lots of polar atoms arrange themselves all in the same way, it creates a magnetic domain. Magnetic domain, which is like an area in a magnet where they're all facing, where all the poles are facing the same way. It's called a magnetic domain. And then sometimes in really very good magnets like this one, this is a neodymium magnet, and really good magnets like that one, they all the domains face the same direction. Now this is going to take a long time because I have to keep switching back and forth between markers, but you see what I mean, right? Let me start just drawing arrows. We're drawing arrows in the direction of north. If they all face in the same direction, if all the atoms in here line up, that would be a super strong magnet. Even in this one, not all the atoms are lined up. Probably most of the domains are more or less aligned. In my very weak dinosaur magnet, there's probably some real outliers here. They may all, on average, be facing roughly the same way, but on average, they're all facing roughly the same way, which gives it magnetism. It makes it a magnet. But it's a pretty weak magnet because not all of them are facing the same way. In Earth, we draw this as, and actually all of these things have what we call a magnetic field, which is this area around a magnet where there doesn't have to be anything. What is here on planet Earth? What's out here? Space. Nothing. Yeah, the vacuum of space. But the magnetic field still exists. Now, do you see these lines? Do you see these lines? No, not in real life. Yeah, in my drawing you do. But in real life, you don't see the lines. This magnet, my bar magnet here, which I keep running into, has the same magnetic field lines. And they are, unlike my drawing, they are three-dimensional. They exist as kind of like an egg shape. I'm sorry, Josie. There's another thing in there called magnetic field plate. It looks like a glass plate about half the size of a piece of paper, and it's full of iron filings and water and stuff. Miranda knows where that is. She can get it. But I want to show you that the magnetic field exists in 3 dimensions. So magnets have poles, and they exert what's called a magnetic field around them. Wes?
You can see magnetic fields from radiation.
You can see the what? Yeah. When you saw the eclipse, how old were you when that happened? 6? When you went to see the solar eclipse that happened around here, and for a second the moon was in front of the sun. For about 7 minutes, the moon was in front of the sun, and you could see something that looked kind of like this. And that was the sun's corona, which you normally don't see because the disk of the sun is so much brighter. But that was the sun's corona in the shape of these magnetic field lines. Exactly right, Wes. So here I have this. I'm going to swoop it up. This is a little plate of mostly oil with some iron filings in it. And you can see, as I let it trickle down, hopefully you can see, where do the filings gather? Yeah, around the poles. And there's some there in the middle that are there because they have fallen. But then if I turn it on its side like this, you can kind of, maybe not on camera very well, but you can kind of, I'll pass it around, you can kind of see that there is a 3-dimensionality to it. That's happening not just in 2-dimensional lines like I have drawn on the board. Let's also put this guy up here. Come here. Oh yeah, that one's going to be so much. You get off of there. You don't even need you. There we go. So the trouble with this one almost has the exact opposite problem where now they're all over here and we can't really even tell. But actually a cool thing is happening here in the distance where the ones that aren't even really very close to it, put it on the camera. You can see that they're starting to align themselves. So these iron filings, the iron filings are themselves not magnetic. Be really careful with that magnet. Do not let it near your computers or your cell phones or your heart pacemakers or your hearing aids. Just if anything is technological, don't let that magnet near it. Your fillings are probably okay. Your fillings are probably made of silver and mercury, and so they're not magnetic. But the iron filings that are in there react, maybe I shouldn't use that word, but they interact with the magnetic field, but they themselves are not magnetic. Those little iron filings have, because they're iron, they could be polar, And so they align themselves with a magnetic field, and that's called paramagnetism. You should write that down. Paramagnetism, which is where it will align to a magnetic field, but exerts none. What does the word exert mean? Yeah, it doesn't itself have, that's a kind of weak word, but it doesn't itself have a magnetic field. It doesn't itself exert a magnetic field. It doesn't cause other things around it to align to a magnetic field, but it will itself align with one. That's called a paramagnet, or the property is called paramagnetism. These ones, by the way, where they are arranged in domains, are called permanent magnets. And these are all in what category of the forces of the universe? Electromagnetism. This is also, in my example of you pushing your sister down the stairs, does anyone have a sister? Here's Peyton. She's got a ponytail. Here's Kylie. Here's some stairs. These are like who stairs, because look at how... Anyway, push. That's electromagnetism. It doesn't seem like it, because you're not like... Let me cover you in metal, Kylie, and then drag you out here with a magnet. But it is electromagnetism, because what's happening when you push something, nice. When you push something, the reason your hand doesn't just go right through it is because of the electrons in the atoms in your hand repel the electrons in the atoms in the magnet. The reason you can sit in a chair and not go straight through it, remember, atoms are mostly empty space. I think we've talked about this. Maybe you talked about this when you were in 7th grade. But if the atom were the football field, the nucleus would be like a basketball in the very middle, and the electrons would be like a pea on the very far edge of the football field. It's mostly empty space. And so, but the reason you don't just phase through your chair is because there's a repulsion. There's electromagnetic repulsion there. So any push that you do, I'm trying to look for something I can push without breaking. Sage! No, I'm just kidding. I did actually push it, though. This push, even if you don't knock it down, this push is because of electromagnetism. That's because of electromagnetism. It's because the electrons in my fingers are repelling the electrons in Sage's, what I would call it a hydro flask, but I'm not really up on things. That is because of electromagnetism. So what we think of as the normal contact forces are really electromagnetism. Nothing ever touches. My fingers don't actually touch this. That's not quite true. That's kind of a science teacher's old wives' tale. Because like if you get stuff glued to your fingers, that glue is actually chemically bonded to you, and so it's touching as much as anything in the universe is touching. What happens if I break this magnet in half? Now I have a magnet that only has a north pole and a magnet that only has a south pole. Is that right? No. What happens? Let me give you another analogy. Let's pretend instead of this being a magnetic dinosaur, this is your, I'll just erase this part. This is your cat. Does someone have a cat in here? Yeah. Who has a cat? What's its name, Sage?
They got names.
Okay, who has a cat that they love? Tegan, what's your cat's name? This is going to be lovely. Spook. So say I cut Spook in half. Does this half of Spook have a back?
No.
Yeah, it does actually still. I mean, let me show you. The back half of Spook here, I mean, there's like some guts coming out, but the back half of Spook on the front still has a back, right? If you cut something in half, it still has a front and a back. If you cut a magnet in half, it still has a north and south pole. There's no such thing as what's called a magnetic monopole. A magnet can't have only one pole. It doesn't exist. Every time you cut a magnet, now even though if I were to cut, where'd my red and blue one go? If I were to cut this one in half in the shop downstairs, right along this line, even though one side would only say north, it would still have a south pole, right? You see, the paint is not what makes the magnet a magnet. Someone put this on here so it would be convenient to look at. Not because here I am trying to snap it in half like a Kit Kat bar. Not going to happen. The paint is on there as a convention. That doesn't determine which side is north and which side is south. It would be totally possible, especially with that very good strong magnet, to reverse this. So the north pole was what said south. The paint has nothing to do with it. If you cut this in half, you still have a north and south pole on both sides. So that's magnets in general, I would say. Let me make sure I didn't miss anything. There's another property that I guess matter can exhibit called dimagnetism. There are others too, but dimagnetism is where it inhibits magnetism. Let me show you an example of this. I need, for this, Miranda, would you run in that magnet box, there was a huge chunk of copper.
Oh, yeah.
Yeah, would you get that? So the dimagnetism, I guess maybe I shouldn't say inhibits magnetism, but it reacts with a magnetic field in a way that causes, really what it does is causes eddy currents in these little atoms that are making it up, and they slow or prevent a magnetic field. Thank you. So here we've got a chunk of copper, which is dimagnetic. Chunk of copper. Let me have that. Where's that good strong magnet? Wesley, give me the good strong magnet. Also, I'd be really interested to see how having this good strong magnet next to my brand new microphone is going to ruin everything in my life. So here I've got, good thing it came with two. So I have this object here, this non-magnetic pin cap, right? I'm going to make a little ramp. Oh no! And in case you think that was because of that it was rolling, that it fell down, let me get something that won't roll. I wish I had something that didn't roll and wasn't magnetic. Sage. Oh, my pocket knife. Here we go. Not magnetic. But now I have this magnet. Isn't that sick? Isn't that sick? I want you to, once again, keep this away from your instruments of technology, like my microphone. But I want you to like drag this over. This is the coolest. I love this. I think we talked about this last year, so I think you already know what it is. But do try it. It's so cool. It's so cool. Keep it away from your stuff. One thing that is very useful, and I've alluded to this a couple of times, that we can do with magnets is we can make technology out of them. A lot of technologies need magnets. I don't know if you are aware of this, but the way that the speakers in your Beats by Dr. Dre, is that still cool? What's cool? AirPods. Is that cool? What's cool? What is cool? Mr. Snittley's headphones. The way that the speakers in Mr. Snittley's headphones work is that there's a diaphragm that is magnetic, and there's another magnet, and in response to an electrical current, those magnets move, and that causes vibrations in the air, which your ear hears as sound. That's how speakers work. Microphones, almost the reverse, where there's a diaphragm in here, and the sound of my voice pushes that diaphragm closer to a magnet, and that generates electrical signals, which then the computer receives and stores as something like the sound of my voice. We'll see later. But that's how magnets work for speakers. Check that out. That's pretty sick. Both speakers and magnet. And another thing they can do is, you should write this down. This is a very important and fundamental truth of the universe. Let's write this down. Magnets moving in a conductive. What kind of conductive do you think I'm talking about of the two kinds? That is not a word I was expecting to hear. What kind of conductive do you think I'm talking about? What are the two kinds of conductivity? Things can be either, they can conduct heat or
Magnetism. And
electromagnetism, which is, we would say, if it's conducting that, we would call it a conductor of electricity. Good. So in this case, I'm talking about electrically conductive. Magnets moving in an electrically conductive medium generate current. Someone's lab showed this. I think it was Cody and Lucas and Brinley showed it, that when you have, what they had was a spool of wire. Is that something like the truth, Cody? And you had the two ends of it connected to an ammeter. And then they dropped a magnet through it. And as the magnet moved through this coil of wire, it read some number of amps. It wasn't very many, maybe 1.2 amps. I don't know. It probably wasn't quite that many even. 1.2 amps. It registered that a current was starting to flow through this wire. Well, how did that happen? The answer to that is one of the most important discoveries of, I think, probably the 1800s. But it was discovered that you can generate electricity by moving a magnet. So that's exactly what this does. This is a little generator. A generator is what we call an object that does this. An object that's built to develop a current by the movement of a magnet is called a generator. Have you ever experienced like a generator at your grandpa's farm or someplace, or maybe you have one in your house? And like, there's such a thing as a gas generator, and it's loud, and you can't put it inside because it'll kill everyone. But what its job is it moves a motor. I'm sorry, I shouldn't use that word. In the engine, it moves some pistons through the same process as what we talked about in chapter 6 about how the internal combustion engine works. But it moves some pistons, and those cause a magnet to move within, kind of like this, within this wire, and that generates electricity. And you can plug stuff into it, and you can run what I used to do at my grandpa's farm is I would use the generator to run a shop vac, and I would vacuum out the seed drill, and that was my favorite job. I loved vacuuming out the seed drill. But there wasn't power there, and so we had to use a generator. So there's different ways of making the electricity. There's different ways of causing the movement of the magnet that generates the electricity. Wes?
It's also how some of us get our electricity by high pressure.
Yeah, exactly. That is exactly what I was going to say. There's different ways of making the magnet move within here. Lots of times we use something called a turbine, which is like a spinning wheel. There are wind turbines. The turbine is also how in a coal power plant, what happens, you didn't know this about Santa's workshop, but coal, when it burns, gets really hot. They use that to boil water, and the steam that comes off that boiling water is under enough pressure that it will spin a turbine, which causes this to happen, which generates electricity so all the good little boys and girls can get their Beats by Dr. Dre or whatever. You can also do it with your hand. This is a generator, and within there, you can see it's clear so you can see what's happening. Within there, it's moving this little, inside this gray thing is a magnet, and that magnet, as it moves along the conductive medium, in this case probably a brush, it'll cause a current to flow through these wires. Let's check it out. These, a lot of times I will break these on accident, so don't let me do that, Tommy. Thanks, Tommy. Here I've got. Don't let me break it. You hold this. Don't be on the camera, but hold them separate from each other and make sure that thing is on the camera. Your hand can be, but not your face. Do it. I'm going to pick up my pocket knife in the meantime. My lid. On the camera. Hold it up in front of the camera. Way up, up. Okay, a little bit more up and to my right. No, higher. There we go. Oh, lower. There we go. Look at that. Higher. There we go. Look at that. I made the LED light up because I'm turning the crank, which is causing electricity to be generated. The electricity, like we talked about in the last chapter, is flowing through the wire, and it's causing the LED to light up. You guys see that? That's sick. Try this. Yeah, that's, in a way, that's true, Wes. I think I'm part of it, Tommy. Okay, hold these. Do not let these touch each other because it'll ruin the whole thing. And then you have to crank it this way, the way that I'm doing. If you're holding it like this, crank it towards yourself like that. And don't do it too much because if you get too much voltage through there, it'll blow out the LED, and that will ruin it for everyone. The opposite, or the reverse of that, is this little guy. I wish someone brought me a 9-volt battery, even though I never asked, and there was no way for you to know that was going to happen. A 9-volt battery. The opposite of that is this little motor. So the reverse thing is true here, where in this example, we had a magnet moving causes electricity to flow. But if we have the same setup, but we put electricity through it, the magnet will move. Okay? So they're almost reverses. Let me write this down where I had my magnetic domains. Tell me, what kind of energy change is a generator causing? From mechanical, specifically kinetic, to electric. And a motor does the reverse. Electric to kinetic. So in one case, the magnet, and let me ask you a question. Do you see why a magnet is important for this? Remember, the magnet's special property is that moving through a kinetic or a conductive medium generates current. And current going through the medium generates movement. Where'd my battery go? It's on the table. Good. Okay, so here I have the opposite, you might say, of a generator, which is this little motor. I'm going to put, I wish I had a piece of tape or something so you could see what was happening. Nice see-through tape so you can see what's happening. I'm going to put a piece of see-through tape on here. Here's my nice piece of see-through tape. Come here, camera. You can really tell. Gosh dang it. If I was just a tiny bit more prepared. I'm coloring my see-through tape red with dry erase marker, one of the normal things people do. And then I'm going to put the ends of the wire. I'm going to put the ends of the wire. Come on. Check it out. Look at that. You can't see it at all. And what's inside of there? What kind of thing is inside this motor? A magnet. Usually the way these work is kind of shocking me. You can do it if you want. It's not going to hurt you. It just gives you a little bit of a shock. But usually the way these things work is that instead of a coil, some of them do have coils of wire, but sometimes instead of a coil of wire, they will have conductive brushes. And that both generators and motors can have those. But brush and brushless motors, yep. Do you have questions about generators and motors? Do you have questions about the reason there are magnets in general? It's just magic. I mean, it's not that far from magic. Once you learn about something, it starts to seem less magical. But don't let that happen to you. It's a time of year for magic.